Okay, the next talk is ProtoPCB, reclaiming printed circuit boards erased as prototyping material from Jasmine. So let's start.
Hello, I'm Jasmine Liu. I'm a PhD student at the University of Chicago, and I'll be talking about this research project called ProtoPCB, reclaiming PCB e-waste as prototyping material. This work was done in collaboration with Rishitha, Boddu, and Pedro, Lopes. So in this work, we explore building tools to allow the printed circuit boards that often become e-waste to be reclaimed by applying computer vision and computational search methods, and find ways of prototyping new circuits on these existing PCBs, such that PCBs are no longer fixed designs, but actually can be used to prototype a ton of new systems. Before diving into the work, I'll give a very brief primer on PCBs. So when prototyping with electronics, you might employ a variety of different approaches depending on your experience level and needs. But when it comes to where you build your circuit on, there are four main approaches: breadboards, protoboards, breakout boards, and printed circuit boards. So these first three are probably the most common to early prototyping stages. If you go into any lab that is prototyping with electronics, you'll likely see shelves of them with a mixture of these. This is because these three types of boards are inherently reusable, so you can anticipate using them for a bunch of different electronics projects. But using these boards severely limits the type of designs you can prototype with and the types of components that you can use. Which is why much of the electronics industry is still using PCBs. There are a few reasons, but important to know about PCBs is that they are absolutely necessary when working with surface-mounted components, which make up the vast majority of electronic components. And PCBs are also manufactured for a specific design, allowing for these highly compact form factors and flexibility for specific constraints. However, PCB's biggest strength is also its biggest weakness. So this PCB here was designed for a handheld game controller. It's only doing that, and that's why it's so neatly packaged together, very compact. The same game on a breadboard is much clunkier. So the benefit of PCBs here is that they're designed to enable these surface-mounted components, but they're also designed to be single-purpose. The process of prototyping with PCBs can be extremely time-consuming and wasteful, however. This is a small portion of what we had in a class learning about designing PCBs that Pedro Lopes, right here, teaches at the University of Chicago. And what's more, these PCBs are not easy to make. For the most part, and including for that class, people are sending these PCB design files to manufacturers. So it's a very involved process from design to manufacturing to shipping. Now, given that PCBs are so time-consuming and wasteful to work with, our approach looked instead of manufacturing a new PCB for every prototype, we explore how you can actually reuse already existing PCBs to prototype new circuits. Now, even a super talented electronics engineer would have a pretty hard time identifying how to optimally reconstruct a circuit on a PCB meant for an entirely different purpose. But with ProtoPCB, we built a tool that computationally solves for how you can implement the new circuit onto existing PCBs, making this process a lot more accessible. So I'll demonstrate quickly how our tool does this for the circuit. The user is about to use our tool to fit this new circuit design onto an existing e-waste circuit board. Here, the user is going to load in their schematic and also the e-waste board files that they have around them, and they'll hit Run Circuit Match Analysis. After some time, once full circuit matches are found, ProtoPCB is going to render the best circuit match, showing the user where they would solder components to, as well as where to make interventions, like adding a wire or cutting a trace. So how does that search process actually work? So we're using computer vision to analyze two layers of the board, the copper traces layer and the solder mask layer. The copper shows how all parts of the PCB are connected, and the mask shows where you can actually solder components to. So first, we're going to look at the mask layer to identify places that components can be connected to a board. To find ways of physically fitting the components onto the board, ProtoPCB is searching using a mask of the component footprint and scanning across that initial layer to look for intersecting areas. Using this approach of these intersecting geometries, we can widen matches to go beyond these one-to-one direct component matches, to also include matches within another footprint, as well as matches across different footprints. Using this sort of approach, we can find a bunch of different locations where components can be soldered onto the boards, regardless of whether or not those locations were actually originally designated for that specific component. So here I'm showing how a 5x5 timer that has a pin layout like this can be soldered onto an existing PCB 16 different ways. And for even simpler and more common footprints like this resistor, the number dramatically increases. Now there's over 300 different ways that you can solder that component onto the board, including at the end, if we see here, putting a resistor on an old USB footprint. So now that we know how we can solder components to the boards, we then turn to leveraging the existing traces on a PCB to realize how to connect all those components together until the reused PCB is able to realize a circuit that it was never designed for. So using these trace layers, we create a mapping of all the board's connections, considering the traces, pads, and vias that are all connected. And with this information, we can start our algorithmic search process. First, we identify a component to start with, usually the one with the most pins, and look for a component placement match. Then we take a look at one of the nets touching that component and look at the relevant pin. We consider the pads and traces touched by that net, and then try to find possible component matches for all the other components in that net. We continue to repeat this process over and over again until the circuit is completed. So this sort of simple, greedy search process is going to do its best and find as many ways as possible to fit the new circuit onto an existing PCB. But sometimes it's just going to be physically impossible to do so perfectly because of a missing connection or creating a short. And well, ProtoPCB will also identify ways to use interventions to implement a circuit in these cases. So we also do searches for where you could add a wire, cut a trace, or use multiple boards and stitch them together. So again, pulling it all together, our GUI displays all the possible ways of implementing that new circuit onto an existing PCB. And net by net, a user can see where to solder components to, what underlying traces are used, and where to make those interventions. So those were a great many strategies for retrofitting a circuit onto an existing PCB. Now in practice, how well would this work? We took a look at 9 different boards of varying complexity, and pair by pair, we looked at how often you could retrofit a board circuit onto another one of those PCBs. And these were all open source PCBs, and they all have like really different purposes. So on the left, we have a table showing when the boards could be implemented on another board, either as a full match, where all the components could be soldered onto the board, or a partial match, where a portion of the components could be fit. In blue is the specific cases where only interventions would be needed to complete a full circuit. So those would be adding a wire or cutting a trace. On the right, we show how for each circuit, what percentage of components could be fit onto another board on average. And across all of these PCBs, an average of 81.7% of components could be refit onto a different board. So we found that really exciting and showed how viable this approach of reclaiming PCB e-waste could be for building most types of circuits. So to conclude, whereas originally one PCB was designed for one purpose, by applying a suite of computational methods, we can find a plethora of new ways to reuse these PCBs. And this process of PCB reuse can kind of keep happening on this same board. Today I'm talking about ProtoPCB, which offers this whole new prototyping strategy that allows us to also harness a lot of the benefits of prototyping with PCBs, but by also minimizing the waste inherent to that prototyping process. This new strategy was completely conceptualized by prioritizing reuse and examining how we could support it. From there, these really interesting research questions emerged that forced us to rethink how PCBs were made and what limitations they had. And by thinking within these constraints of waste and what we already have around us, this very different fabrication pipeline emerged, and I think there are so many other directions this computational approach to PCB retrofitting can totally take, and I hope this will just be the start, and that more researchers will be inspired to find new approaches alongside ours. ProtoPCB is a part of an ongoing thread in my PhD work about computational recycling, exploring how computational methods can inspire new tools and systems for better recycling e-waste. So alongside reusing PCBs, I've also explored a tool to assist reuse of electronic components and how to think of recycling along the stack instead of our default bulk recycling approaches that is common today. So these works were heavily inspired by each other, and new ideas around reuse are continuing to pop up all the time with every new method. So I encourage the broader HCI community to also consider how they might approach building tools for computational recycling. Thanks so much for listening to this talk. I'm happy to take questions now if we have time, but I also have a lot of talk after lunch that you can ask me questions at, and I'm demoing the system during the reception tonight.
Great. So one question is possible. So maybe.
Hi. Thank you very much for your talk, and I think that you are raising a super important matter here. But I was wondering, what happens after you identify the ways the board needs to be altered? Like, are you gonna just pretty much solder additional components, or like desolder others? Like, is there any way to automate the process?
That's a great question. Yeah, I would, like, for ProtoPCB, we primarily envision it as like a hand soldering thing, kind of small scale. One cool outcome of our software tool is that we can actually identify solder mask or stencils so that you can make the process a lot easier. But a way to automate it would be just like being able to put this in an oven, scrape off all the components, yeah. And like, I think there are a ton of ways that this could be integrated in a larger scale manufacturing pipeline. We haven't explored that yet, but that's something we're actively thinking about.
Thank you.
Thank you so much.